In episode 73 of Mobycast, we start a new series on encryption and dive into the essentials. Welcome to Mobycast, a weekly conversation about cloud-native development, AWS, and building distributed systems. Let's jump right in.
Welcome, Chris and Rich. It's another episode of Mobycast.
Hey
guys, good to be back.
Yeah, great to have you back. So, Chris, what have you been up to this week?
Well, as I think I've mentioned several times on the podcast, I'm a cycling nut, and the month.
No spoilers, please. I'm like a couple days behind.
Oh, come on. Okay, fine. So
I'm
be
serious. Serious as a heart
attack. Okay. Okay. Yeah. Well, let me just say, it will not disappoint as far as like just drama.
Okay, I'm excited.
We'll put it that way. It's kind of amazing. Just the last few days.
I'm almost done with stage 18. They're about to start up the Galibier, so that's where I'm.
Okay. Yeah. So July is definitely the month of Tour de France, and so our children, my wife is equally a cycling nut, at least when it comes to following the pro peloton. So during July, we joke that our kids become tour orphans because it's quite a bit of commitment to 4 or 5 hours of coverage every day. So we're done, except we actually are behind on the final stage on the Champs-Élysées. By the way, we subscribed to DirecTV to watch this year. So you just do it all over the inner tubes. Mm-hmm. Don't have to, go have cable installed or get a satellite dish. But the software is just absolutely horrible. And they keep saying it's in beta, but it was in beta last year when we got it. It's just awful and terrible. We've had so many snafus this month with trying to record it and it dropping recordings and not recording things, and NBCSN, for some reason, on yesterday's stage, the last stage, they decided to switch channels midway through. So,
oh my God.
Because we set up our DVR, right? We got so we're watching it. We think we have the whole stage, and then it's like, no, it's missing the last hour. They're like, oh, alert! Switch over to NBC to see the rest of it. And it's like, but we DVR'd it.
Oh, that's so terrible.
So anyhow.
Well, it's only going to get worse probably because I think a lot of the DirecTV developers are in Denver, and there's a new shiny thing in town for them to go work for named Slack.
Yeah, well, we're done with it. I am canceling today. So,
how about you, Rich? What are you up to?
Oh man, we've been busier than we've ever been, and so the idea of project portfolio management is becoming pretty important. And what that is, and I didn't really know what that was until a couple months ago, is like the bird's eye view of all projects. So the idea of using Gantt charts and trying to figure out how you can jigsaw puzzle human resources so that you can layer projects in creative ways that you can get more done. So trying to figure that out, which has been challenging because I don't have any experience with project management. So I'm learning as I go. But I mean, I think I'm we're not at a point where it's already a problem. So I'm sort of doing this ahead of time, but nonetheless, it's challenging to sort of put that hat on and be effective when you don't know what you're doing.
Yeah, well, you and I have talked a little bit about it, and I'm excited to see your journey.
Yeah.
So, and I just have a quick story too. I had to get a new file cabinet, and I had bought one on Amazon, which don't do it because I spent like $250, and some freight company came and dumped like a totally dented piece of trash on my lawn, and I had to let it sit there for another month while I waited for the freight company to come back and get it. So do not do that.
You could have taken it to Whole Foods.
Yeah. Simply drive over a mountain pass to get to Whole Foods. Anyway. Yesterday, I saw one on classifieds, and it was $75. And I went down there, and I met the guy in this fancy neighborhood called Cordillera to pick it up. And I was like, "This is really seeming like a good deal." And I walked up to it. He had it in his driveway. I walked up to it proprietarily, looking like, "Oh yeah, I'm definitely going to buy this." Opening drawers, and he's like, "Yeah, I don't know why my wife put this up for sale." I asked her, and she said, "Well, it doesn't have any files in it." And I was like, "But you're putting it up for $75? And he goes, "That thing costs $1,300. So I was like, "Oh, maybe I should be a little bit more polite and thankful and not just like, yep, I'm taking it."
Was it plated in 18 karat gold?
No, but it's like, I don't know. It's pretty fancy. Honestly, it's solid wood file cabinet. It's pretty fancy. So I'm excited. I just got it moved into my office. But that's not what we're talking about today. Let's talk about encryption. Everybody depends on it. Everybody talks about it all the time. And I think it's one of those things that's not very well understood. I was just having a conversation with one of our clients over at Zupix the other day, just trying to talk. We're implementing this new direct messaging feature, and we want to make sure it's really locked down. And we were talking about the difference between end-to-end encryption and just making sure things are encrypted at rest and in transit. And it was quite an explain. It was a lot to talk about and make sure that my client, who's not a developer, who's a business person, was able to understand and make decisions around, because this affects his budget and the company's budget, and they want to spend their budget wisely. And the people listening to the podcast, I think you probably know a bit more about encryption maybe than my client, but there's so much to it, and it's so fascinating that I think we should get into it and talk a little more in detail. Do you want to kick us off, Chris?
Yeah, absolutely. So, yeah, I mean, like I said, encryption is one of those things we just kind of take for granted. It's there. It's kind of underpins so many things that we use, like the web. Like we know that things like HTTPS is like pretty important whenever we're transmitting anything that's sensitive information, whether it be credit card information or social security numbers or whatnot. And so we know, I mean, like encryption it definitely is just so important. We know it needs to happen. But for the most part, I think it's a bit of a black box for most people. Like, how does it really work? And what are the different types of encryption? And so that's what we're going to talk about today, is just we're going to kick it off with, this is going to be a multi-part episodes on encryption. But to start off with, we're just going to talk about just the essentials of encryption. You know, what is it? What does it mean? Encryption in rest versus transit, the various types, the major types of encryption, and how they work. So hopefully it's going to be pretty interesting and kind of fill in some of the gaps that folks have out there about just like, what is encryption and how does it work and which type should I use?
You know, when I was in college, I remember there was sort of a demand among my peers in our computer science classes. There was demand. Everybody was interested in it. I can't remember which class it was where it was introduced. I remember John Rager, the professor, was the one that taught us, and he taught us public key encryption and how it worked. And I remember he said stuff like, you can't, do not share what I'm putting on this board with anyone, because I've just written down something that would be illegal if you were to go share it with certain other people. And we were all like, whoa, this is cool. And I think the reason was because it's got this reputation of being hardcore. Like when you're doing encryption, that's when you're starting to get hardcore with computer programming. Would you agree, Chris?
Well, what I would agree is that the actual cryptographic algorithms are intensely hardcore. I mean, it is math at its purest, and it's incredibly complex. People do their PhDs on. I mean, it is very, very difficult, because you're trying to come up with an algorithm that is going to be very, very difficult to reverse engineer, to crack, right? And given how fast computers are evolving, and things like Moore's law and transaction, the ability to how many operations per second computers can do, it's up to the algorithms to become more complicated and to have more entropy in them, and to, the data, slight changes in data. Like if you want your cryptographic algorithm to have like big changes on the output, right? Like you don't want to be able to find patterns in it. So having a really good, strong cryptographic algorithm is like very hardcore, right? Like you need the PhD in math, and it's teams of people, and like this is like weapon level quality, right? I mean, this is government, national security, right? So governments put lots and lots of millions and millions and millions of dollars behind this kind of stuff. So absolutely. But the good thing is that we don't have to, like the normal, people using encryption don't have to know the exact details and the proofs behind them. Right. We can pop up a level or two.
Well, and I think it may be instructive, especially for anybody that's kind of newer listening, is that, so I remember seeing an NSA catalog in the computer science office at my college. And I think if I had seen that thing before I learned the cryptographic algorithms, I might have been like, whoa, cool. NSA is super cool. Cryptography. Yes, I want that. And I might have applied. But fortunately, I saw the magazine, the pamphlet after we learned the cryptographic algorithms. And just, I remember learning them and being like, Yep, I don't think I could spend a lot of time thinking about that.
It took all that excitement, that sheen, that super secret agent 007 away from it, right?
Right. Yeah. So, but using this stuff is not that hard, as you just said, and it's so important. So let's talk not about how the algorithms themselves work, but rather, the practical use of this stuff, because that is not only not hard, but absolutely expected and important.
Right. Exactly. Yeah. So maybe just starting off just like with the definition, right? Like what is, encryption? What is it? And, really quite simply, it's the process of taking some plain text and you convert it to something that looks like gibberish, right? It's ciphertext. So you're just transforming your information that you want to be kept secret into something that bears no resemblance to what it originally was, right? And so that we call that ciphertext. Some of these encryption methods require a key, and that's kind of key to the whole encryption algorithm, right? It's a secret that's known, that's part of that transformation function to change that plain text into ciphertext. And use cases for encryption are many, right? I mean, at the end of the day, it kind of boils down to you have information that's sensitive, and you don't want other parties that shouldn't be able to see it be able to understand it. So, cryptography kind of has been going on for thousands of years, right? And in various forms, and it's been, when again people, governments, civilizations have secrets that they want to keep within their ranks and they don't want to share it with others. So whether it be a codex or like the example of in World War II, the kind of trying to send communications amongst the different armies, so England trying to crack the transmissions from Germany and vice versa, and like this has been going on for a really long time. So that core use case of I need to basically make this message secret so that other people only, the people that I want to be able to decode it can, is at the core of it. So just about everything we do today, has use cases for this, whether it be, again, like we're sending our credit card information over the internet, whether we're storing sensitive data on a database server, we want to have secure communications point to point between ourselves and someone else. So things like WhatsApp, that's one of its big features. It's encrypted communication between users. The WhatsApp servers can't even read the messages. It's only the recipients that can read it.
And I think it's bear saying that even stuff that doesn't seem to need to be encrypted really should be these days. Almost, it's like encrypt all the things. And the reason you should encrypt all the things is because bad actors, whoever they might be, are able to tell so much from context now that if you just encrypt everything, then they can't really tell anything. So even if all you're doing is looking at cheese making recipes, hey, put them on HTTPS. That way, whatever bad actor might need to know something about you can't use the fact that you were looking at cheese making recipes the day before as a way of kind of triangulating what you're up to. Mm-hmm. So encrypt all the things.
Yeah, I mean, it kind of sounds silly, right? But it's like with machine learning and AI, like patterns and so, I mean, it's like that actually, that context can actually end up becoming kind of useful and whatnot. Mm-hmm. So, and I think, in the past, we didn't necessarily encrypt all the things just because there was such a performance penalty to it. And it was also a lot more difficult. But now it's so simple to do. It's so easy. And there really is very negligible in the way of performance. So in fact, you're seeing most of the major browsers now are moving to the point where they're kind of requiring that communication. The web traffic is over TLS. It's secure, and they're showing warnings if it's not over a secure port. So encrypt all the things. Werner Vogel's CTO for AWS is kind of famous for coining the phrase "dance like no one is watching, but encrypt like everyone is," right? which is a good one.
Yeah. All right. So I guess we're going to talk about 3 different types of encryption now, starting with hashing.
Yeah, maybe before we get into that, why don't we talk a little bit about just where to encrypt, right? And so this is where things, terms like encrypt in transit and encryption at rest come into play. And like it kind of makes sense, I think, just to talk about those 2 things in general. So, and it really kind of boils down to like, again, what is it that you need to secure, and when are you going to use one or the other? So encryption at rest, quite simply just means it's data that's encrypted at where it's stored. So it's wherever it's persisted. So whether it be in a database or a file system or whatnot, it gets encrypted before it's actually persisted. And so that in its restful state, it's encrypted. And then when something wants to read it, it reads the encrypted data and then decrypts it to now get to be able to inspect that data, right? So that's encryption at rest. And so again, anything that you're persisting, you're storing like in a database. So it could be like you're storing credit card numbers in a Postgres table, right? Those need to be encrypted.
Or it could be just encrypting, cute pictures of pets and things that people say about them, which is what we do on Zupix.
Sure. Yeah, absolutely. And again, encryption at rest is one of those things that in the past was much more complicated and expensive. And now in the cloud native world, it's one of those things where literally it's a checkbox option. And it's like, why not do it?
And people get Twitter pylons if the checkbox isn't automatically selected.
Yes. And then we have encryption in transit. So this is just the data is moving, right? So it's going from point A to point B. And as it travels from point A to point B, it's encrypted. So this is really to protect against things like eavesdropping. And, whenever you're like anything over the internet, any kind of traffic, right? It's like you do not have a direct pipe from your machine to whoever's machine it is you're talking to. You're going through many, many hops along the way. And you're going through many different servers and routers and whatnot, right? So there's always the possibility for eavesdropping there. There's also the possibility for folks to spoof destinations and to kind of redirect traffic. So because of that, encryption becomes really important when you need to protect that. So encryption in transit is just the data's moving, it's going from point A to point B, and as it does, before it gets sent over the wire, it gets encrypted, and then the receiving end, when they receive it, they can then decrypt it and read it and make sure that only the recipient has the ability to decrypt. So that's encryption in transit.
Great. Now we're going to talk about types of encryption, and you can tell us about hashing.
Yes. Yeah. So we'll talk about three kind of main topics here. So the first would be hashing. Definitely, this is one of those core foundational aspects of encryption, but it's not encryption necessarily in and of itself, right? So hashing is really it's an algorithm that, given an input, so the thing that it is that you want to protect, you pass it through this hash algorithm, and it outputs some obfuscated hashed value, right? Or something called a digest. And so it's a one-way function, right? So the same input to this function will always produce the same hash. But because it is one way, it's impossible to do the reverse, right? You can't, given just the hash value, you can't go back, the opposite direction to recover to get to the original data. So it's a one-way function. And then also a good hashing function will, giving the particular hash value or a digest, it's going to be infeasible to create another string that would produce that same hash value, right? And so that's called a collision. So that's kind of a common term that people may have heard, like hash collision or whatnot. And so that's really just where you have two different keys or input strings that produce the same hash value. That would be a collision, right? And that's bad. And so a good hash function will make that very much infeasible. That it's the likelihood of that happening is just very, 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 very low, right?
Right. I guess that is important, though. It definitely does happen, and I think even the best hashing functions have, for any given hash, there's infinitely many ways to make a collision, but it's just really unlikely, right? Like, because there's infinite potential data inputs, and so you can keep trying them until you get another one that produces the same value. Because the values themselves are not infinite. Like they may be 36 letters or 30. I don't even know what to call it, but they may be 36 long or 48 characters long. And so there's only so many of those, but there's infinite possible inputs. So therefore, for each one of the potential outputs, there are infinitely many ways of achieving it.
Yep. Exactly. And I think that the important thing with these hash algorithms is usually the way and when these are used in practice, what ends up becoming kind of important is just the actual hash digest itself. That's what's used to figure out whether or not like this is the correct value that you want. Like that is the secret, right? So the hash algorithm gets applied by two different parties, and if they come into the same result, right? So
yeah, that's totally what it's for. Is like, can I trust that this thing is the same as this other thing?
Mm-hmm. So if you do have a collision, then that kind of that's a really bad thing, right? Because it means you don't need to even know the secret, right? To be now where the other side thinks that you do know it. And so again, a good example would be a password. I mean, if you had a really bad hashing algorithm for your passwords, and if I type in my password is foo, and someone else tries to guess it and guesses bar, and it turns out that foo and bar both hash to the same thing, then the server is just going to say, oh, you have the correct password.
Right.
They don't, right? But the hash value was the same. So that would be an example of a collision, and that would be wrong. And that's a really obviously simplistic that
When
we
I
don't
think
do.
about when I think about hashes, I always think about the graph of the function. I think about like the x-axis as it goes along. Those are all the different potential inputs. So from 0 to infinity of inputs. And the y is like the hash that comes out of it. And I just imagine this like almost solid thick line, because every time you move, one increment down the x-axis, your output value is way different than the one that was right before it. So it's just like this, like up and down, up and down, up and down, all over the place. Function.
You should not be able to plot a curve.
Right, exactly. Right. So that's what I think about. I don't know if that helps anybody that thinks in terms of math, but I think about that.
Yeah, complete entropy is really what you're going for here.
Mm-hmm.
Yeah. So yeah, some examples of hash algorithms are SHA, SHA, MD5. And then bcrypt is a specific hash algorithm that's specifically designed for password hashing. And so bcrypt is something that, as developers, most developers, I think, are pretty familiar with bcrypt, and especially if you're dealing with passwords and storing passwords and whatnot. So that is a hashing function. It's based on the Blowfish cipher, and it also incorporates a salt into it. And the salt is incorporated to protect against brute force hacking. And so this is again kind of interesting. First of all, I mean, think about all the different security attacks and hacks that we've heard about even over the last 5 years. And so you have the really bad ones where services, they stored passwords in clear text, right? Which okay, that's kind of really hard to understand. But then you have systems where they hashed the passwords, but they weren't salted, right? Mm-hmm. And so I think really famous is LinkedIn. So the LinkedIn password hack, I think it was in 2012, they stored their passwords as hashed values, but it wasn't salted, right?
So I want to just explain what that means. Like, so the input value, I guess you've been calling that the key. So say it's geranium or pizza dough. To every single one of those input values, before hashing it, they'll add like XYZ or 1234, just some salt, a few extra characters. And then they'll add those 1234 to the end of geranium and then hash it. And then so when a person types in their password, they type in geranium. Again, to make sure it's the right password, the system will add 1234, that same salt to it, hash it, and see if it's the same as what it was stored earlier. So that's what salt is.
Right. Yeah. And so, if you don't do this, what it means, so imagine we're just using the bcrypt algorithm. We're not giving it any salt. Let's just say we're not using salt for whatever reason. So we think we're doing the right thing. We're using bcrypt, we're encrypting we're hashing these passwords and storing the hash values. They type in geranium, it generates the gobbledygook. We think we're doing well. And that's all fine and good until someone else, the bcrypt algorithm, it's well known, anyone can use it, right? So what they can do is and this is the rainbow table attack, right? So really what it is just a lookup table. So you just go through and just start picking passwords. You run them through the bcrypt algorithm. You now have the hash value. And now all you have to do is, if you've got a a dump of hash values that represent passwords, you just use your lookup table. And once you find a match, now you know what the actual password is, right? Because it's just the same algorithm.
Mhm.
And so that is a rainbow table attack. And that's what led to the issue with like the LinkedIn problem back in 2012. So SALT is basically, it's an extra secret that's applied to the algorithm that's very specific to that particular service or application, and it has to guard that very closely, right? Like that ends up becoming the actual true secret here. It really is like for all intents and purposes, it is the key in that particular case. And so without that, then with that SALT, it's basically it's a new rainbow table, right? And so unless you know that specific key, you're not going to be able to do that same kind of brute force password attack. So always SALT with your your hashing with that.
Yeah, as tempted as I am to go into it, I won't, but I'll just sort of leave listeners with just also that hashing cryptography is what's used for blockchain as well. So this thing that we just explained is kind of at the core of how blockchain works and Bitcoin and all of that.
Hey, this is Rich. Please pardon this quick interruption. We recently passed an internal milestone of 50,000 listens, and I wanted to take a moment to thank you for the support. I was also hoping to encourage you to head over to iTunes and leave us a review and/or a rating. Positive feedback and constructive criticism are both incredibly important to us. So give us an idea of how we're doing, and we'll promise to keep publishing new episodes every week. Okay, let's dive back in.
And so kind of really interesting too with bcrypt. Bcrypt actually, the standard allows for, it's an adaptive function. And so as part of the algorithm, you can tell it how many iterations it needs to go through to compute the actual hash value. And so they do this so that you can make it slower as computers get faster, right? So it makes it more resistant to the brute force search set. So kind of similar to like how Bitcoin works, right? You can just make the algorithm more computationally complex as needed as computers get faster and faster.
Super interesting.
Yeah, that was something I learned the other day as well.
Cool. All right, should we talk about symmetric key encryption?
Yeah, so now we can get on to basically the two main encryption mechanisms. So there's symmetric, and then there's public key, which is also known as asymmetric, right? So let's first talk with symmetric. So with symmetric key encryption, you have a single key, right? So it's the same key is used to both encrypt and to decrypt the data, right? So which means that in order for secure communication to happen between two parties, both parties have to know that same key. So lots of different algorithms out there that use symmetric key encryption. So things like AES, triple DES, Blowfish, RC4.
Everything was symmetric. Everything that you could decrypt was symmetric key encryption before the invention of public key encryption, right? Like
yes,
secret decoder rings, everything.
Yeah. I mean, going back to back in World War II, when the Germans were encoding their messages, they were creating a key they had a daily key. They rotated their key daily, but it's symmetric key, right? So they had to have a way of all parties needing to know what that key was, and as long as you had that key, you could then decrypt the message, and then they would rotate it every day. But yeah, absolutely. For symmetric key was the way to go. Was the only thing really up until the early 70s, I think, when came up with a more secure way of when you have to, so that you don't have to share one single key, which again has its limitations, and we can talk about that a little bit more.
Do you know anything that you can share? I don't want to get too mathy, but you mentioned 3DS, AES, Blowfish. Those are ones we've heard of. Do you know anything about generally how, kind of like a high level, what the math is doing? Again,
at the very highest level, it's a function, right? It's like you have an input, you have some algorithm that translates it to an output. It's very similar to like what we talked about with hashing. So you want to have the most entropy possible so that there's not patterns there. You refer to these algorithms as being spongy. It's sponginess of basically how much information can you soak up in your algorithm and kind of hide it from the output. So,
Okay.
but
And that's, I guess the unique thing about them is you've got two functions, one that can produce this output, another one that can take the output and regenerate the input from it.
Yeah. Very, very low level math. I mean, it's just, and again, it really kind of boils down to the harder the algorithm is to crack, the better the algorithm is, like the more complicated it is, right? So like you could have a really simple algorithm, like the key ends up being like you shift the character by 3 or something like that, right? Like a simple rotation, right? Or something like that. But so simple, not very complicated from a math standpoint, but also really easy to break. So that's where the complexity of these things come into play, is that, again, they're trying to increase that sponginess of it. They're increasing the entropy of it. They're also getting to key lengths that are obviously the more bits that are there, the more possibilities there are, which makes it much harder to do from a brute force attack. So that's why, I mean, I think the original DES was like 56-bit encryption, and then triple DES is 3 times that, right? And so AES was 128, and then, now the standard is 256-bit. So more.
And I know it has something to do. So what I think we should do, because I know it has something to do with prime numbers, and I know that there's some sort of like intuitive way of kind of understanding what's happening. So maybe we can come back to that in the next episode and just spend 2 or 3 minutes in the next episode explaining kind of at a high level what's happening in some of these algorithms, because I think it'd be interesting for people without getting into the details of the math. And then the other question I want to answer that I imagine we're not quite ready for is, I have not fully understood how we do things like make sure that something that's short is just as impenetrable as something that's longer. So if you have a tweet and you encrypt it, well, that's only going to be like 256 characters max, or 240 characters max. So what are we doing to make sure that it's really impenetrable? Because 240 characters doesn't seem like that many to be guessing, or even fewer sometimes. Like, if you have a chat transcript, somebody might answer with 1 word. What are we doing to make sure that, if somebody keeps answering yep, that we're not able to be like, oh, now I can see what yep is, right? So a couple of those I'm kind of curious if we can have intuitive answers for in the next episode.
Yeah, and I mean, a lot of that just boils down to how you use encryption, right? This is more like up to the application itself and like what's important. So, in that particular case, like you may decide that you do it in batches or something like that, right? To kind of add to some randomness, because the algorithms themselves, like, again, you're feeding them some input, it's going to give you an output. And if the input's always going to be yep, if that's all it is, that you just keep encrypting, then that may be information, right? I mean, it's just going to be the same cryptic output, like with a hash function. Some of these, I don't know specifically. I mean, some of these encryption schemes may involve randomness in the form of like time or something like that as well, and that would feed into it, which might kind of help there. But yeah.
Let's revisit.
Cool. So that's symmetric key encryption. And so again, the key part there, no pun intended, it's kind of hard to say that, right? Without using the word key. The important point there is that both parties have to have that key, right? So the big limitation with symmetric key encryption is, how do you securely get that key to everyone that needs to be able to read it, right? And that's where it gets kind of complicated. That's with the management of it, and then also just worrying about like what happens, will that get exposed?
Yeah, I think it's safe to say that it requires trust. I think, like, in order to truly have symmetric key encryption, you have to have at some point, the transaction of handing keys to each other involves a little bit of trust. You have to trust somebody. Like, there's actual personal trust involved in
yeah,
that.
I mean, a really probably good example is passwords. Like, sharing your password with someone, like, better trust them, right?
Right. But in order for us to have a conversation, so say you and I want to have a symmetric key conversation with each other, we have to exchange this key with each other. We have to, at some point, figure out a way to trust, yep, it's really me, and I'm really giving you the key, and now we can talk over it. And like that, I'm bringing this up because I think that's a good it's going to be our segue into public key, which gets rid of that requirement.
Yeah, so let's talk about public key encryption, which is also known as asymmetric key encryption. So in this particular scheme, right, we have this would be common terms like people have heard before, right? Is you have a public key and then you have the private key, right? So the public key is published. Anyone can see that. And that is generally used to encrypt messages. The private key is only known to the receiving party, right? To basically the owner of that key pair. So they're the only ones that have the private key. So when you do this public key private, so someone wants to send a message to you, they go first and find out, okay, well, what's your public key? And so they get that. They now use that to encrypt the message, and now the message is sent, right, to the user. So basically, that part's not secure, right? So anyone can see that message, right? And the message won't necessarily be secure because it's the public key used for encryption is known to everyone, right? But what happens is only the person with the private key can actually read the message.
Right.
The decryption can only happen with the private key. And this is the public key, private key, the math behind it. This is based on prime numbers, right? And that's how those two things work together, and where the math is involved is it has to do with prime numbers.
Right. So that just makes it possible for people to be able to communicate with me without me knowing who they are and without even trusting that they are who they say they are. It lets them give me a message that only I can read. And that's so important. Like, I think one of the best use cases that's happening all around us today is just, whistleblowers getting information to journalists. Who knows who the whistleblower might be or what they're working for, but they need to be protected. And the journalist wants to tell that story. And so the whistleblower will use that journalist's public key to send a message that nobody else can read. So maybe they can tell that a message got sent. Maybe they can see the gibberish, but nobody else can know that the whistleblower is saying, this important secret meeting took place between these public figures. Only the journalist will be able to tell that that's what happened.
Yep, exactly. Yep. Yeah, and you kind of hit there some of the other issues with like just trust and identity and, making sure that the public key that you're using is indeed who you want the recipient to be. That's kind of important. So kind of examples of public key encryption implementations are SSL, TLS. So the key fundamental encryption method for the web, right, is public key. Other ones are like RSA. PGP is probably one of the first implementations of this, which stands for pretty good privacy. And that was back in the early 70s. So again, public key encryption, big improvement where you don't want to share secrets amongst parties, but yet you can still set up this guarantee that only the intended recipient can actually read the message.
Mm-hmm. And there's one even further thing that we don't have in our outline, and I can't describe it very well, but I can give basically the gist of it, which is being able to sign something with public-private key cryptography. Essentially, a person, if I'm wanting to talk to you and you don't know who I am, I'm going to use your public key to encrypt some stuff and send it to you. But I also want to prove to you that I really am who I say I am, or at least that I have the key that I say I do. Because I guess somebody else could have gotten my key, but that I really do have that key. So, and I can do that by signing the message that I send to you with your public key. And I can't remember exactly how that works, but essentially what it boils down to is that there's some way that I can use my private key and your public key in a way that only I could do. It's like basically encrypting my own public key with my private key or something like that. But basically nobody else could do that but me because I'm the only one with my private key. And on your side, you can see, oh yeah, it must have been John that did that, because when I decrypt this with my own key, my own private key, I can see that it turns into his public key, which only he could have done. So it's essentially basically like giving you my public key in a way that only I could do. And I don't know exactly how that works, but that's super key to making sure that people can not just have conversations without trusting each other, but also kind of identify themselves. Like, I am who I say I am.
Yep. Yeah. So signing of secure messages or any messages, basically it's kind of like the reverse, and exactly what you just talked about. So, and that's a way of kind of a further check to kind of say, yep, this is coming from whoever it is that I expect generated this message did do it. And so in what we just talked about with public key encryption, where the sender uses the public key to use the encryption. When they sign it, they use their private key for the encryption. And so the recipient is using the public key to decrypt the signed portion of it. And it's using their own private key to decrypt to get the actual message contents. Right. So,
and the key here isn't knowing exactly how the sausage is made, but knowing kind of what the use cases are. Because obviously, listening to this, you might be like, oh, Chris and John certainly aren't encryption experts. And no, we never claimed that we're encryption experts, but I think we know enough to keep ourselves out of trouble. And we know enough, I think as a developer, if you're making decisions on how to do something, how to implement something, there's sort of an area where you need to know at least this much to make sure that things are safe and that the data that you're, when you tell your client or you tell your boss, this is safe, we've done the best practices. You need to get yourself above that. But then, as in everything, there's diminishing returns. So why haven't Chris and I gone and why aren't we able to tell you every detail about each algorithm? It's because it really isn't relevant to our day-to-day job. It doesn't actually, it's not something that we would make use of day to day. So we'd rather spend that same time, learning about new features of AWS or learning about different aspects of business or what have you. So it's kind of getting above that threshold. And that's what we're hoping to do is get you sort of to our level of understanding cryptography with these 3 episodes, and then you should be all good.
Absolutely. Yeah. So I think, kind of a good stopping point for this particular episode. And next time, I think it'll be fun to kind of dive a little bit deeper into the practical implementations of encryption and kind of just doing a walkthrough, how do these things work? And so things like TLS, SSL, what's really going on there? How does that actually work and generate secure web traffic? Look at how do you do secure point-to-point communications where servers can't see the actual message because it's encrypted, that the encryption decryption is between the recipients only. And how do you handle the case where if you have multiple recipients, which is kind of an interesting situation. And we'll also get into the practicalities, what happens in the real world. It's not symmetric key encryption versus public key encryption. It's usually you use both of these. And there's reasons for doing that because public key encryption is very computationally expensive. Symmetric key is much less so. So how can we use these two together in concert to have a really secure but also performant way of communicating?
Very cool. Looking forward to it.
All right, guys.
Thanks so much. Talk to you next week, Chris and Rich.
See ya. Well, dear listener, you made it to the end. We appreciate your time and invite you to continue the conversation with us online. This episode, along with show notes and other valuable resources, is available at mobycast.fm/73. If you have any questions or additional insights, we encourage you to leave us a comment there. Thank you, and we'll see you again next week.